Please be seated. Good evening, ladies and gentlemen. I am Wynand Steyn. I am the Dean of the Faculty of Engineering, Built Environment and Information Technology. And I would like to welcome our Vice Principal Academic, Prof Loretta Ferris, our speaker this evening, Prof Charles Siyasiya, members of executive and fellow deans, Prof Natasha Nodia, who's the head of department for the Department of Material Science and Metallurgical Engineering, other academic professional staff and colleagues, and as I always say, especially those that's not in the faculty. There are some of our colleagues that's really interested in learning about other stuff happening at the university, so welcome to you. Then also very specifically the family of Prof Siyasiya. It's wonderful to have you over here. We normally don't have our families on campus, but it's always good to share with you also what we are doing. You are really welcome here tonight. Ladies and gentlemen, it is always a privilege to host these inaugural lectures, and very specifically the one this evening with Prof Charles talking about advances in steel design and processing to curb greenhouse emissions. As I indicated, our DVC academic, Prof Loretta Ferris, is here tonight. Please join me welcoming her to formally open the event and introduce our speaker. Thank you.
Good evening. On behalf of the Senate of the University of Pretoria, it is my privilege to welcome you here this evening at the inaugural lecture of Professor Charles Siyasiya of the Department of Material Science and Metallurgical Engineering here at the University of Pretoria. Before we begin, I would also like to specifically recognize Professor Siyasiya himself, members of his family, and in particular his wife Daisy, his sons Maya and Caleb, and his daughter Taco. I also want to acknowledge any of my colleagues in the executive, the Dean of the Faculty of Engineering, Built Environment and Information Technology, Professor Wynand Steyn, the management of the faculty, then friends, colleagues, mentors, peers, everyone who has shaped Professor Siyasiya's career up until this point, and then he particularly wanted us to welcome his postgraduate students who are here this evening. So we are delighted that all of you can share this occasion with us and with Prof Siyasiya. Of course, at the University of Pretoria, we are very proud of the Faculty of Engineering in particular, and that our degree programs have been accredited by both national and international statutory bodies. At present, the Department of Material Science and Metallurgical Engineering is the leader in this field in South Africa, in particular also because of the quality of our academic staff, the quality of our programs, and I think the quality of the students that we attract. But because I think more than ever is the fact that we have academic staff such as Prof Siyasiya who are exposing future professionals in this area to the full scope of the discipline. Whether it's minerals processing, pyro and hydro extractive metallurgy, physical metallurgy, welding and corrosion metallurgy. And this extensive exposure is also the reason why we are able to prepare graduates for industry and collaboration across all of the sectors between industry, government, research institutions, etc. enabling them as professionals to ensure that industrial equipment functions well and that material properties are optimized. So when senior academics at the University of Pretoria are promoted to full professorship or appointed to a position of academic leadership, they are required to do this. They are required to deliver an inaugural lecture. It's an auspicious event in the life of an academic, and it's also an event that we want to share not only with our peers, with our colleagues in the department, in the faculty across the university, but we also want to share this moment with collaborators that may be outside of the institution. For example, collaborations with government, collaborations in industry. But more so than sharing it with the people that understand the discipline, we also want to share it with our family, because we know that, that they have to sacrifice the time that they would have spent with our academics because of the fact that they dedicate their life's work to their particular discipline. And for us as a university, the inaugural address provides us with an opportunity to showcase the scholarly work that we do at the university. It celebrates excellence in academia. It gives the speaker a unique platform to share their achievements in research, innovation, engagement, and teaching. And of course, it's an indelible part of the heritage and the history of academic institutions. And academic institutions have been doing this for hundreds of years. So let me then talk a little bit more about Prof Siyasiya. His academic career has channeled him into a life of iron and steel. And of course, just talking a little bit about iron and steel in particular, since the Industrial Revolution of the 1800s, the use of iron and steel has become increasingly significant in terms of global consumption. In recent times, in pursuit of sustainability and stemming the impact of climate change, there has been a focus on reducing the energy consumption required for steel production, while at the same time making ever stronger and tougher steel. And this is where the work that is conducted by Prof Siyasiya becomes important. So in his inaugural address this evening, he will share with us the advances in steel design and processing to curb greenhouse emissions. He will also share with us his current research into hydrogen storage and repurposing of the existing storage and transportation systems, and present some future perspectives on the role of green hydrogen as an alternative to coal in producing what is called green steels. So this will be, Prof Siyasiya, a significant moment for us, because we know that we are struggling with the impact of climate change. And part of the mission of this university, the vision and its mission, is to contribute to solutions that are troubling not just our continent, but that are troubling the world. So Prof Siyasiya started his career in Malawi, where he graduated with distinction with a Bachelor of Science in Mechanical Engineering in 1991. He thereafter joined the Malawi Packing Industries Company, but in 1999 he joined academia when he was appointed as a junior lecturer at the University of Malawi. He joined the University of Pretoria in 2002, enrolling first for an honours degree and then a master's degree. And then after graduating with his PhD in 2007, he joined the Industrial Minerals and Metals Institute as a physical metallurgy researcher in material science and metallurgical engineering here at the university. But then he moved back into industry for a few years, where he joined ArcelorMittal, during which he acquired valuable industry exposure and experience. But I think he decided that his purpose is in academia, and so he rejoined the University of Pretoria as a senior lecturer in 2010. He's taught undergraduate models modules in material science, as well as postgraduate modules in basic physical metallurgy, green heat treatment of steels, and welding metallurgy. He says that 40% of his research focus on ferrous metals and the pursuit of less energy and lighter steel components for improved payload and carbon footprint. Another 40% focuses on new non-ferrous materials and processing technologies, and 20% on hydrogen and materials research. So you can see that he very much is looking in different areas, but through the lens of mitigating the impacts of climate change. And he says that this last research, the research on hydrogen, will likely continue to grow due to the need for decarbonization through the development of materials and technologies to meet the reduction in CO2 emission targets for 2050. Prof Siyasiya is also involved in interdisciplinary research, and one project in particular he is running in collaboration with the Dental Technology Department of the University of Technology of Durban, which involves the recyclability of metal waste from dental applications. As a senior academic, Prof Siyasiya has to date supervised 9 PhDs and 18 MN students to completion. And we are also privileged to have here this evening some of his current students. I hope that this evening and the lecture that he will present to us inspires all of you to greater heights, and most importantly, to join us here as the next generation of academics at UP. Prof Siyasiya is also a prolific publisher. He has authored and co-authored 50 journal articles, 46 conference papers, and 2 book chapters, and he holds an NRF C3 rating. He is a registered ex-professional engineer and a member of the South African Institute of Mining and Metallurgy. Above all, however, he stresses the importance of family, and it is very special that his wife and children can share this evening with him. Finally, on a personal note, he says that he loves to run, although not marathons, fixing old cars, and experimenting in the kitchen, specifically lentil with dishes. He says when it comes to lentils, he's a firm believer that with a good engineering mind, the recipes are endless as long as one has a wide range of vegetables and herbs. So on that note, let me give over to our guest of honor, Professor Charles Siyasiya. Thank you.
Good evening, Professor Ferris, the Vice Principal, Professor Stein, the Dean, Professor Koch, the Head of the School of Engineering, Professor Natasha Nodin, the Head of Department for Material Science and Metallurgical Engineering, Heads of Departments, colleagues, friends and family. Tonight, I'm going to present to you advances in steel design and processing to curb greenhouse emissions. That's my outline. I'll talk about steels in our lives, then the advances that have taken place, my contribution, then I will give you a small, view of where we are going in terms of transitioning from traditional steels to green steels, and then I'll conclude. So, as you may see here, steel has got a wide range of applications, from birth to even death when you are descending in the grave, for those of us who don't cremate. And everything in between, steel is part and parcel of it. And therefore, it is my personal conviction that steel is going to be with us for a long time. And I have all the reasons to study steel as long as I am here. So, until the 1970s, affluent civilization existed without advanced computers. And that was possible because of these 4 materials that are consumed in large amounts. And second on the list is the steel at about 2 billion tons per annum. And these 4 materials contribute to 20% of the global emissions. And out of these 4 materials, 50% of the emissions come from steel. This is a familiar sight on South African roads. It looks weird, isn't it? The whole truck just carrying 1 coil. And that coil weighs, it can weigh up to 30 tons. So therefore, this is a full truckload. And it can be as long as 2.5 to 3 meters long. And its production emits 60 tons of CO2, an enormous volume of about 33,000 cubic meters of emissions. So there must be a different way of producing steel. So there are 2 methods, well-known methods. The first one is the traditional route, where you use coal. It decomposes into carbon monoxide, and it reacts with the iron ore to give you iron plus some carbon emissions. All right, so it's carbon dioxide, that's the greenhouse gas. And this accounts for 95% of the steel production as things stand now. But there is an alternative route which is aligned to Sustainable Development Goal number 13 on climate. There now hydrogen is used to reduce the iron ore, and the byproduct is water, which it can be, that water can be recycled back, or we can use it for domestic purposes, bathing, washing. That's the sustainable way of producing steel, and this is called green steel. So a bit of, let's define some terms here so that all of us can be on the same page. So iron is a metallic element, and it exists in iron ore. And this is an open cast mine, and what you see here is just iron ore. And it accounts for 5% of the Earth's crust. So you may ask, why steel? Why is it popular? It's because it is available in abundance and versatile, wide range of properties, and it is also recyclable without losing its value and properties. Above all, it is relatively cheap. Greenhouse gases, they are known for trapping heat in the atmosphere and therefore causing climate change. And out of that, CO2 is the main culprit. So green hydrogen is produced from water by splitting the water molecule using electrolysis. But the energy must come from either wind or solar. It must be clean, renewable energy. So green steel is produced using hydrogen, and as things stand now, that accounts for 5%. So let's just go back in time. What you see here is a simple iron smelter from the Iron Age, and this is from Burkina Faso, so it's African. Metallurgy also, came from Africa. We made our contribution. So it was very, basic, just a few kilograms per day, and after the reduction of the iron ore, or what you get is some iron grains, which were, hammered at relatively high temperature just to get a few hand tools. And therefore, there was no need to be concerned about carbon emissions because production was low. And this was followed by the blast furnace. So the blast furnace was invented in China in about 200 BC. and entered Europe in around 1100. So since then, the fundamentals have remained more or less the same, except for the advancements in technology that have ushered in some good efficiency and as well as improved capacity. So here I'm just showing you a modern blast furnace, and with an output of 15,000 tons per day of crude steel from just, a couple of kilograms. Here I'm just illustrating, the charge. There you have iron ore and coal, and you are charging the blast furnace. You tap iron, and on the other side you are tapping out slag. So blast furnaces produce iron, which is high in carbon content, and therefore is too brittle for most engineering applications. And therefore there is need for a second stage to process this, crude, this steel, this iron, to reduce the carbon content. And this is what limited the application of iron prior to 1800. And in the middle of 1800, the Bessemer process was invented, and it revolutionized the production of steel and lead into the second industrial revolution. This is just a schematic diagram, and 100 years later, it was replaced with what we now know today as basic oxygen furnace, in short, BOF. So up to 1950s, energy consumption and CO2 emissions were not a concern because production is very low. And here I'm just showing you now charging of a basic oxygen furnace, and that's the pig iron from blast furnace for further, reduction in carbon content. So as things stand now, this is what we have today. We have the traditional coal route and the hydrogen, but mostly also the natural gas, which are hydrocarbons. And if hydrogen is going to be used as a reducing agent, this will be now the process route. So it will be direct reduction iron, which is DRI, then electric arc furnace, and you end up with crude steel, which is processed further. And the steel design starts here, where now the steel is tweaked to fit purpose. Then after that, it is cast, then rolled into long products, the products that we see, flat sheets for iron sheets, pots and pans. That is done here now. So from here now, I'm going to show you how steel can be designed and processed to curb greenhouse emissions. So once the steel is cast into billets and slabs, in this particular case I'm using an example of slab, it is rolled down into sheets using a hot strip mill. So what I'm showing here is just the last 7 stands of the hot strip mill. Prior to that, there is a roughing mill. All right, so, and after the slab, so at this stage, this slab is about just, can be up to 30 tons and about 250 millimeters thick, 12 meters long, and the width could range between 1 meter to 1.5 or even 1.7 meters wide. So it is rolled down, and between these two stages, between this hot strip mill and the final product, there is cold rolling that takes place here. But this is now the final product. So my ferrous research is split into, especially that is focused on hot strip mill, is split into alloy design of the rolls, and this is one of the major consumable on the hot strip mill. So it's alloy design and heat treatment, 20%, and the other 80% is focused on alloy design of the steels that we use every day, as well as the hot working itself, in order to minimize energy input as well as carbon emissions. So the entire process from slab casting all the way to the final product we use contributes about 20% of the carbon emissions that are produced in the entire steel making chain. So here I'm just illustrating to you a schematic illustration of the 7-stand hot strip mill. The first 4 stands use what we call high-speed steel rolls. And these are the wick rolls that I'm focusing on, because these are the ones that wear faster because they're in contact with the strip, the steel strip. And you have, of course, these backup rolls, which can weigh up to 60 tons. But my focus is on this one. So, as you may see here, the first 4 stands use harder and long-lasting rolls, whilst the last 3 stands use what we call indefinite chilled double pour cast iron, in short ICDP rolls. It is softer, special properties, non-sticking, anti-cracking, so that the final product can meet the required quality. Now the question was, can't we combine the 2 properties so that we have long-lasting finishing rolls in order to curb greenhouse gases? Because this is what the Japanese are doing here in South Africa. We didn't even have a single roll of that nature. So these rolls take about 20 days to cast, 100 hours of heat treatment, and they come at a price tag of over R1 million each. And they are produced by a handful of countries in the world, South Africa being one of them. Here, right here in Vanderbilt Park, Sarako is producing these rolls. 80% of these rolls are exported to the West, US and Europe, a few to Asia. So the leaders are the Japanese, Nippon Steel. And you may ask why so low? It's because for a long time we have only had 1 grade of high-speed steel roll and a small variety of ICDP rolls. So research collaboration started in 2020 just to improve the situation. So we set ourselves 2 objectives. The first one was to introduce one more high-speed steel roll for the first 4 stands. That would, last at least, 20% more, life. That would give us 20% more life. And then to replace the ICDPs with something like graphitic high-speed steels that could last, 3 times the current one. So using materials modeling software, Thermocac in particular, these alloys were designed for objective 1, and these alloys were designed for objective 2. So the spin caster was set, and spin casting was done. So spin casting is the same as, centrifugal casting. And so when the shell was cast, this unit was, is flipped into vertical position, and the spheroid or graphitic iron core is cast inside there, and thereafter you do the machining of the final roll. So this is what you see. So what was done next was to use this huge iron ball to smash these shells so that we could get some samples, and sampling was done. And using a scanning electron microscope, which was dispersive spectroscopy, these microstructures were obtained. So objective 1 was achieved by simply refining the carbides. So what you see here, this is a solidification cell. So this is at micron level. So this is a solidification cell, and you can see primary carbides along the solidification cell, all right? And what we managed to do was to break these carbides into fine carbides and also make sure that they are distributed inside the solidification cell. Because one of the fundamental principles in physical metallurgy is that when the microstructure is fine, a finer microstructure will give you better mechanical properties. So this was done, and hardness measurements were taken. Obviously, the optimized one was emerged as a better product, not only because of the hardness, but because of the fineness and the distribution of the carbides. So production commenced in 2023, and the final evaluation will take place next year when the rows have run a full life. So that's the expectation, that there will be an improvement of about 20%. The second objective was met by introducing fine graphite nodules in the high-speed steel. So you see here is the ICDP with coarse graphite nodules. So fine graphite nodules in high-speed steel means we have been able to combine the properties of the two rows to give us the product that we are looking for with optimized properties. So for this one, 2 rows were cast just this year for trials at ArcelorMittal van der Bouwpark Works. We're expecting an outcome sometime in 2026 when they have also run the entire life. And in the meantime, we are going to do some controlled twin disc tests to study the wear mechanisms as we're expecting the outcome of those trials. The other way of also, reducing the carbon footprint in steels is to replace niobium with vanadium. So why vanadium? It's because vanadium is sourced locally. We have got huge reserves of vanadium here in South Africa, if some of you didn't know. And the other advantage of vanadium steels is that they are softer, and therefore you don't require high mill loads, lower slab reheat temperatures compared to niobium steels. And because they are softer, it is very easy to control the mill, no twisting of metal, and that's what we call cobble, and therefore less recycling of defective metal, and therefore improved carbon footprint. Besides that, vanadium is cheaper. So this can be done by optimizing the coiling temperature. So what you see here, so prior to that we have this hot strip mill, and the strip is coming out and it is coiled here. And the coiling temperatures can range between 550 to 700. And during this time, this steel is still going through phase transformation, and you can optimize the mechanical properties during the coiling process. And 2 steels were selected, and the coiling process was simulated using this machine. It's about 37 years old this year. It's what we call the glebo, and you can use this deformation schedule to simulate the hot working as well as the coiling. And after that, the transmission electron microscope was used to study the 2 steels, the microstructures of these 2 steels. Without necessarily going into details, you can actually see that this is like a basket weave-like microstructure, what we call acicular ferrite. And this is polygonal ferrite plus acicular ferrite. So combining these microstructures plus very fine carbides, this is vanadium carbide, which is less than 100 nanometers in size, and combining it with titanium, niobium carbonitrates of that size, it was possible to optimize the mechanical properties and be able to achieve equivalent properties in vanadium steel. And even the elongation, it was within the acceptable range for these applications. And elongation is a measure of toughness. So it is possible to do that. And we took it a bit further just to look at the evolution of the microstructures with coiling temperature. As you may see here, for the niobium steel, the grains still remain fine, but for the vanadium, the grains are growing, which means not good properties. And to compensate for that, the fine vanadium carbides were able to make up for the loss in strength due to the coarsening of the grains. And the data that was used to generate these inverse pole figure maps was also used to characterize the substructure, and out of that it was possible to conclude that both steels at this coiling temperature are just partially recrystallized as measured by the low angle grain boundaries here. So the question that we need to ask ourselves, where to from here? Because to be frank with you, all these efforts have just, reached a limit. The past 20 years, everything has been, tried to reverse the trend in terms of carbon emissions, but it is not possible. These are just a few examples because we don't have time to go through everything that I have done in the past 15 years here. So for the past 4,000 years, the production of steel has been carbon intensive. And it would appear we have reached a point of diminishing marginal returns. We need to do things differently. So going forward, green steel, it would appear that's an answer. As of now, European countries are busy, funding research in green steels. For example, last year when I was in Germany, and even this year as well through my collaborators there, they are now considering solid state reduction in two-stage reduction of iron ore. So first it will be solid state reduction using hydrogen. Then they are experimenting with a second stage, which is hydrogen plasma, so that they can achieve efficiencies that are achieved through the conventional way of doing things. So green steel with less than 90% carbon emissions offers us hope. This picture is from one of the largest producers of steel in the world, that's China. Yes, we may say that the carbon emissions have dropped significantly over the years, but what is alarming is the escalation. It's almost exponential growth in carbon emissions because of the great appetite, the huge appetite for steel. So that comes at a price of increased carbon emissions. This is just a picture of how things are. This is coming now from the climatologist. I'm not a climatologist, I'm just a metallurgist, so I'm taking it as it is here. So you see this is the carbon emissions as a function of time over the past 50 years. And the main culprit here, look, it's CO2 emissions. And steel contributes 10% of the global emissions. So those who study climate project that by 2050, there will be a temperature increase ranging between 3 and 5 degrees Celsius. And with these two interventions, it can either be 50% reduction of the current carbon emissions, or 80%. If it is 80%, then it will be just 1.5 degrees Celsius by 2050. So if we look at green steel, with a reduction of 90%, that is a contribution from steel making, we could be looking at this trajectory. This is now from the climatologists. So as we stand today, this is where we are at. One path with enormous carbon emissions, and the other path, the hydrogen path, with 90% less carbon emission. But this also comes at a price. You look at the energy input. Because carbon is a source of energy when you use it in steel. When you replace it with hydrogen, then you are taking away that source of energy. Therefore, you must input more energy. So it doesn't come free. And that energy must be clean, renewable energy. That's where the catch is. At this point in time, we don't have capacity to sustain the steel industry. However, there are projects like Namibia-German project, which is currently ongoing. Why Namibia? There's sun, there's water, and there's wind. So all the resources are available there. And this also appeared on our website here at UP, the news about potential natural hydrogen reserves in Mpumalanga. If that materializes, then there is hope for us. So this is the hydrogen energy industry chain. It starts from production. It could be at a site somewhere, and the end user sits somewhere. And this has to be transported, all right, from the end user from the producer to the end user. So there are two ways of doing it. It can either be transported in pressure vessels or pipes in the form of compressed gas or liquid hydrogen. It can also be transported via the solid state, as a solid state product. However, there are pros and cons, and we see that there are more pros for the solid state hydrogen storage and transportation. And that's why there is so much interest today in solid state hydrogen, storage and transportation. So here I'm just showing you the laying of this pipe. It was done a while back from Mozambique to South Africa, to Secunda, to be specific. And this is the line pipe. And these steels, they suffer from what we call hydrogen-induced cracking. And in South Africa, we have 4,100 kilometers of line pipe network. And mostly it is concentrated in this region here. And these pipes are made of titanium niobium steels, namely API X52. API simply stands for American Petroleum Institute, and X52 stands for 52,000 pounds per square inch. So these steels are designed to carry fossil fuels under high pressure. So the question that we need to ask ourselves, can we repurpose this for hydrogen transportation so that we can deliver hydrogen to a kitchen somewhere in Mpumalanga, and maybe someone making a living by the roadside, can we deliver this safely? That's the question that we need to answer before we even, think of repurposing this, this infrastructure. So in order to do that, we need to understand the chemical composition and properties of these steels, and for X80, that's the chemical composition, and the yield strength is about 550 megapascals, and the elongation must be about 21%. So in order to do that, we need to understand the microstructures. So you may have already seen microstructures similar to these ones. It's this, we get these microstructures by using electron transmission microscope. But what I want you to focus on is the fact that these steels exhibit complex phases, and therefore these phases must be optimized in order to achieve the desired properties. And here I'm just showing you the cooling rate. So it's temperature versus time, and this is now cooling rate, and showing how the microstructures evolve with cooling rate. So after we have understood these microstructures, the next phase is what can we do to this steel in order to improve its resistance to hydrogen cracking. So there are surface treatments that can be done. So for example, for the existing line pipe steels, one can use surface coatings. You can also introduce compressive residue stresses on the surface, because we know that compressive residue stresses impede diffusion of hydrogen. So in this exercise, in this study, not exercise, but in this study, what we intend to do now, after we have understood the microstructures, we are going to use laser shock peening to introduce compressive residue stresses. And thereafter, these samples will be tested for hydrogen permeability using this, hydrogen permeability cell. We have just acquired this, unit recently, and this is just used to interface with the computer. And after that, we're going to generate these curves. What would be of interest to us is this time delay. All right, so this time delay is associated with hydrogen trapping. So we'll study the mechanisms of hydrogen trapping and to see how they can be exploited to improve the resistance to hydrogen attack. Last but not least is the solid state hydrogen storage. And as you may see, the figures are, speaking for themselves here. Why there is so much interest in solid state hydrogen storage. It's not only about capacity, but it's also most compact way of storing, hydrogen, and it is the safest. And it doesn't, hydrides don't expire. So I'm just illustrating here, these materials contain hydrides, which can, release hydrogen and absorb hydrogen. So the one category of preferred materials for hydrogen storage is high entropy alloys. So these are alloys with large configurational entropy, and because of their large configurational entropy, you can mix elements, 5, even more elements in equiatomic amounts, and be able to produce a single phase material or a multi-phase material. They've got a wide range of applications, including hydrogen storage. So the hydrogenation thermodynamics is governed by the Van 't Hoff equation that relates pressure to temperature. And in designing these alloys, one needs to take into account all these storage capacity and hydrogenation temperature and cost as well, because the materials I showed you in the previous slide, they are very expensive. So we use tools like computational phase diagram, CARFAD, and here at UP we are using mostly thermocalc and density function theory, machine learning, open source codes and software. And out of this, for example, these graphs which show the relationship between pressure, composition, and temperature are generated using HIPS software. And in this work, after materials modeling, these two alloys were designed, and we procured some powders, and using laser direct energy deposition, the samples were printed, and after printing, materials characterization was done, and using XRD, it was proven that indeed these are BCC materials, but they also contain lattice phase. The lattice phase is also good for hydrogen storage. Literature shows that. So we are yet to prove that. And the next phase now will be to test to validate the hydrogen storage capacity. That will be done using the PCT Pro 2000 machine or its equivalent. We are going to use one here at CSIR, at Hydrogen South Africa. And this is just the schematic presentation of the machine. If you know these two volumes and you know the pressure, if you open this valve, you should be able to measure the hydrogen absorption of this material. And out of that, we are going to generate curves like this. Now, this will be now in practice, and it will be compared to the modeled materials. So this transition comes with challenges, and these challenges must be viewed as opportunities for innovation. So the first one is the increased energy input, and that energy must come from renewable sources. So even in green steels, you need carbon to reduce the melting point of iron. You need also carbon to reduce the risk of iron fines from catching fire, okay, when they are being transported to where they are going to be used. But also carbon acts as an alloying element. And besides that, we know that carbon is useful, has got an advantage in terms of thermodynamics and kinetics of steel making vis-a-vis the stability of the arc, the electric arc furnace, as well as control of inclusions, and even slag formation. Carbon has got an advantage, and therefore that must be also considered if it is going to be taken out of the equation. Downstream processing, thermomechanical processing and modeling, there will be need for new knowledge in that area. But the elephant in the room is the repurposing of the existing machinery and infrastructure. What are we going to do with that? So for me, I've set myself these two research themes as a response to these challenges. I'll look at implications of steel production, green steel production on the evolution of microstructures and texture in ferritic steels, and production of line pipe steels via the electric arc furnace, as opposed to BOF, which is preferred for line pipe steels. In conclusion, despite all the advances that have taken place over the years, CO2 emissions still remain a challenge in steel making. And green steel comes with challenges. But it is, it should be viewed, these challenges must be viewed as opportunities rather than hindrances to progress. Involvement of all stakeholders is critical for the success of this transition. So here the stakeholders start with us researchers, as well as government agencies, NGOs. Everyone needs to be on board. I would like to acknowledge these two professors, Professor Vado Stumpf and Professor G.T. van Rooyen, for mentoring me. As a student, I wouldn't have wished for more. They were selfless. So I thank them. May God bless them in their retirement. They are not with us here. I would like to also acknowledge all these organizations, institutions for collaboration, financial and technical support. I thank colleagues and friends who are here for sharing me with their expertise. There are many students here. I thank you. I appreciate working with you. I thank the organizers for making this event a success. Above all, I would like to acknowledge my family for their support, and I thank God for affording me this opportunity to work in this exciting space. I thank every one of you for coming tonight. I feel honored. Thank you so much. Thank you for coming.
Thank you, Prof Charles, for a very informative lecture on steel and its story. And also the very interesting part of explaining how complex simple solutions to our challenges are. Because we often hear and listen to the simple opportunities of, just use hydrogen for this. Just do it like this, just do it like that. And the way that you also explained that, yes, we can just use the hydrogen, but then we introduce another transportation problem. And then we have to solve the transportation problem. And if we solve that part, then it's a storage problem. And I think what I really appreciate from that is that you demonstrated that something that we see as an age-old, simple process like steel making, and with all due respect to my metallurgical colleagues, I know it's complicated, but we think we've done it for long, so we should easily change the processes. And thanks for the explanation that life is complex in terms of solving problems that may look very simple if we quickly look at them. And that's why we need to develop the in-depth knowledge, the new knowledge, the understanding. That's why for all of the students, there's a challenge for you guys. It's not just something, they solved it, no problem, it's steel, what are we going to do? So thanks for that good explanation. And then I think it would be a miss from me to not show this or discuss this one example of the importance of steel, because we obviously all know about the Olympics that's ongoing, and it's my topic for Professors will know for pretty much everything that I had to present in the last week or two. I've got a way of linking it to the Olympics. If you look at the medals, there's 18 grams of steel in each of the medals. So although you may think that you want the gold medal, whoever designed them made sure that there's a piece of Eiffel Tower steel in the middle of those medals. If you go and have a look at them, that little center part, that's steel. And what I like about that from an engineering viewpoint is it just highlights again that steel is important. It makes life possible, and while it makes life possible, sustainable steel and green steel make sustainable and green life possible. So we cannot just assume we know how to do it, let's just continue like this, because we have to look after humanity and we have to look after our environment. So with that, Prof Charles, thank you very much for telling us the story, and Godspeed in your rest of your endeavors and research. We really look forward to that. I would like to thank Prof Harris for being here tonight and officiating at this. Also, as she indicated, I engaged two of them before we thank you very much for being here this evening. Also, special appreciation. Prof Charles doesn't do a good job, and she's got a lot of work. And faculty does a better job, then she's got Manaka, Suzanne, Tabu, all of you. That's always doing a big job about doing the arrangements for these inaugural lectures. And then lastly, I have to do the marketing. Please have a look. We've got quite a few of the inaugural lectures still coming. I think the next one is next Tuesday, if I remember correctly. And it's always a privilege to actually showcase beautiful work that's being done in the various departments in our faculty and for the rest of the university. We don't always get that opportunity. With that, ladies and gentlemen, please join us for refreshments in the reception area, and I would like to ask you to stand and remain standing while the procession leaves the hall. You must have a blessed evening.